Good afternoon, everyone. So first, thanks so much for inviting me. Really happy to speak here about uh, building private set intersection from function secret sharing, and it has sort of some applications to private contact tracing. So I'll be talking about that today. This is joint work with Sam Dittmer, Yuval Ashai, Ravi Ostrovsky, Mohammed El Sabah, Nikos Kirtis, Brian Schult, and Angela Stavro. Okay, so just a quick intro. I'd like to talk a little bit about, sort of how this lands among other contract tracing schemes, and then talk about the private set intersection sort of construction behind it. So for our approach here, we sort of describe new methods where we increase accuracy and privacy in decentralized contact tracing. And the key insights in our solution is we sort of, for accuracy, we attach sort of these context-aware risk scores to tokens. So instead of just a hit, no hit for the tokens, now there's a risk score associated with each token, and you get sort of an aggregate risk score as part of your tracing query. For robustness, we ensure that sort of a malicious actor cannot relay or replay tokens by tying in location and time with the token. Of course, this is appropriately sort of hashed so that it's not actually being revealed to anyone. And we leverage the existence of trusted hardware on the phone. Contact tracing solutions, I think, have eschewed such approaches, but we were interested in seeing what could possibly be done in that situation, leveraging a trusted execution environment. And then finally, for privacy, and what I've been talking about today, sort of mostly, is a new crypto protocol that hides infected tokens and only sort of reveals the weighted risk score. So just sort of real quick in sort of the landscape of this and how it fits in with other things, right? So for this, right, we're trying to track the risk of infection, not tracking people. So this does not expose the context. It does not expose precisely which token was the one that sort of increased your risk score, but it does sort of tell you sort of the probable exposure overall. We sort of attach additional sort of hardware information or context-sensitive information. Like, for example, if the phone thinks that the person who is sending you the token was behind a wall, or if it's just someone on a bus or just someone just driving by real quick, there's sort of additional hardware sensing to sort of ensure that there is sort of additional features or more accurate data coming in to better give you a risk profile. And finally, we have sort of on our backend a fully encrypted database. Reality is that it's secret shared amongst two servers. For a general audience, we just typically say just it's encrypted. But as you'll see throughout my talk, we'll be sort of working in this kind of two server model. So let's go ahead and look at a comparison of this with and this is a sort of a rough comparison. There are many other features of all of these schemes that I can't even possibly put on the slide. So if I'm not doing any of these schemes justice, especially around one of these is here with you, apologies, but really this is just to get a flavor of what our scheme has, right? So we do not assume a trusted server. We work in the two server model where we also sort of hide the social graph, the server. We sort of hide user to user interaction, so you won't learn which particular token, which particular infected token sort of you saw that actually sort of landed you that risk. We prevent sort of relay attacks where a malicious adversary can have a small sort of scanning device somewhere that collects tokens and then broadcasts them somewhere else entirely. Replay attacks involving sort of time-based changes, right? So storing it from the one location and one time, and then replaying them back at some other time. We also prevent users from omitting any records when uploading their infected tokens or during tracing. Interestingly enough, there's a value judgment to be made here, right? Because if you don't allow people to omit certain tokens when they're uploading, that you might say, oh, maybe it's a privacy feature that we actually allow that. So in fact, this, in the Clever Parrot solution, this is actually lauded as feature. So it's kind of interesting to see different approaches to contact tracing. So for more sort of quantitative or asymptotic comparisons, right? Our work, we have this this sort of communication from user to server, similar to like the EP1 solution, where during tracing, you first have to send some stuff to the server and then you get something back. But what we send is linear in the security parameter to the number of tokens that the user holds. Interestingly enough, the amount of communication back from the server is constant. And this actually is quite similar to the centralized solution. And of course, the user and the server both have to do sort of cryptographic work, but here the work is kind of using only symmetric key crypto and is linear in the number of tokens they each respectively have. And this solution is a one-round solution, and it provides a weighted risk score. And the underlying crypto for this is what I'll be talking about mostly today, which is private set intersection for sort of weighted cardinality. So that's what I'll be focusing on. And for the rest of the talk, I'll be trying to sort of work towards this main contribution, which is we construct a protocol for unbalanced PSI weighted cardinality, which we'll define in just a minute, in the two-server semi-honest model under the existence of any symmetric crypto. So concretely, we use a PRG, but from a theoretical standpoint, it was known that you can sort of construct PSI using function secret sharing in this two-server model. We're really focused on optimizing that and actually sort of applying that towards this application of contact tracing. So you can imagine, the client holding n elements and the server holding some other n, which is sort of much larger than n elements, little n elements. And the performance is that we want the client work to be linear in n, the server work to be linear in capital N, and sort of it's going to be a one-round sort of two-message protocol, right? The client sends something to the servers, and the server sends something back. So along the way of sort of doing this, we have an interesting sort of approach to how we handle sort of hash overflows. So our solution is going to rely on some of the hash-based tricks of private site intersection that I'll talk a little bit about later on, and this actually enables a sort of a new PSI model for sort of streaming PSI that might be of independent interest.
Steve, can I ask a question?
Yeah, please, go ahead.
Hey, so with this cardinality intersection protocol, does the server have to repeat this capital N effort for every client, or is there some kind of amortization across many clients?
Yeah, so that's a great question. This is right. So the way this is done, right, is that between a client and a server, this work is you're basically applying FSS to every single sort of entry for the client. And so because the keys that the client send you are different every single time, you don't get this interesting amortization that you could do for multiple different clients. That is an interesting sort of area to explore about how you can amortize this, where you don't have to basically apply all of your tokens to all the client to the client's tokens every single time. But this is for the sake of this presentation, this is just single client, single client, 2 servers. And if you want to do this for multiple clients, you would have to, at the end, sort of do that work.
Thanks.
Yep. All right. So for the rest of the talk, what I'll be sort of going over is just a reminder of PSI and definitions, a review of function secret sharing, a warm-up example, and then sort of how we actually do our full construction using sort of hashing and streaming, and then finally talk a little bit about implementation and hardening of the solution. So all right, PSI and definitions. So what is private set intersection? Private set intersection is a functionality that allows you to it's a specific sort of special purpose MPC that performs this functionality of revealing only the intersection of 2 parties holding private data. Now, there's sort of many different flavors and nuances that you can go into for this definition, but at a high level, this is sort of what we're looking at, right? So Alice has a set, Bob has a set, and that's the private inputs, and they want to sort of come together and learn only what's in the intersection of those 2 sets, and hiding everything else that's sort of not intersected. And this has actually sort of very interesting applications to a wide variety of areas. You can think of it with applications to the medical field, where you actually want to do intersection on patient data, or even this this application of contact tracing. There's interesting sort of applications to other social research, where you want to study the intersection of various populations to sort of determine sort of correlating factors. And again, it might be on sensitive information, maybe socioeconomic data, maybe education data, things like that. And this has applications even in things like analytics AI, where for example, Google's private join and compute solution, right, where you might even use this for something like sales and advertising analytics. Okay, so to say a little bit more about private intersection, there are a lot of different flavors, I would say, both in terms of approaches of how you actually get private set intersection. So there are, let's say, for example, polynomial-based approaches. There are approaches using sort of hashing, oblivious transfer, and sort of generic secure circuit evaluation of the equality circuit. There are oblivious PRF-based approaches for this. And there are also sort of number theoretic approaches to this as well, using sort of Diffie-Hellman or RSA. So there's a lot of different ways you can sort of do PSI, and there's a lot of different characteristics for each of these. And in addition to the menagerie of approaches, there's also many different flavors of PSI itself. In particular, you can think of sort of malicious PSI, unbalanced PSI, size hiding, and so on and so forth. But what's sort of most related to what I'll be presenting today is this extension of PSI known as sort of cardinality or some PSI. And this has been studied in a lot of recent works, including, there's the work of Google, there's the recent sort of the EPI-1 solution, and sort of more research in trying to produce only the sides of the intersection, or only some sort of weighted intersection, as opposed to just revealing the actual things in the intersection. Right, so this is what sort of PSI cardinality is, right? Where you have, where you want to reveal only the sides of the intersection, but not the intersection itself, right? So it's not entirely obvious that you can just sort of do like a PSI and then get its intersection, because now you're actually hiding sort of more information, as the result. It's only the size of the intersection. And this is, this already, has an interesting application to contact tracing, because, it was observed, right, both in this sort of EPI1, OASIS paper, that and sort of other results, that what we're actually doing here is just sort of counting, or in fact, not even a cardinality, or maybe just even a yes, no, right? Just sort of counting the number of tokens that that are infected, that are also sort of in the tokens that I have seen. And cardinality just provides a count. But what if we wanted to have sort of a richer, a richer analysis? So what if we want to sort of contact tracing with weights, right? So as the phone sees tokens from that are being broadcast from other phones, and by the way, I'm sort of taking sort of the gain, the Google Apple sort of general model as for granted, where phones broadcast these sort of tokens to other phones, sort of viewing things in that model. And now when I receive a token, I can also tack onto that token some additional context, and can view this as a number, for example, right? And so when I actually want to do my contact tracing, I want to do it so that I get the sum of the weights in the intersection, and not just the count of how many things are in the intersection. And so this is sort of a richer thing that you can do for contact tracing, where on the phone, it's the set of tokens I received along with weights, and then on the server side, it's the set of tokens of affected individuals. So the goal is to sort of provide a weighted risk score, and that's sort of exactly what PSI weighted cardinality does. All right, so you might say, well, wait a second, isn't this just PSISum? So let me talk a little bit about how this relates to PSISum, right? For unbalanced sets, when you're doing PSISum, usually the weights are on the server side, but this is a superficial difference, right? PSISum, you can have the weights on either side. I think a more distinguishing difference between weighted cardinality and sum is that you can have weights on both sides, where the weighted cardinality functionality actually takes a sum product. So if you sort of want to define the functionality for this, you can think of Alice having a set of elements, Bob having a set of elements, and the output of this is the sum product of the elements of the weights in the intersection. And just as a side note, here we're not trying to hide sizes. That gets revealed to sort of all the parties. And for the application that we're sort of looking at here, we're only focused on the case where Alice has weights, but the construction can sort of work for having weights on both sides. All right, so that was a brief review of sort of PSI. So let me now go over function secret sharing, right? So what is function secret sharing, and how does this help us build PSI? So function secret sharing is this kind of at a high level a crypto primitive that splits a function f into f1 and f2, such that you have this linear reconstruction property, and individually each piece reveals nothing about f. And for certain classes of functions, like, let's say, for example, for point functions, you can actually build this under the existence of any pseudorandom generator. So point functions, let me just sort of draw this out here, right? It's something that is a value b at some particular point and 0 otherwise. But when you actually do this sort of splitting, it's not revealed, neither the location nor the sort of the height of the point is revealed. And you can sort of see how this can sort of fit in for us, right? Because if you let A be the token and B be the weight, then this is looking like something that you can sort of transform a token on the client side into one of these point functions, and then you sort of apply this function secret sharing to. So in a bit more detail, function secret sharing is sort of a pair of algorithms, gen, which takes as input some representation of a function and produces two sort of shares of the function. You can think of them as just like keys. And then there's an eval function, which takes in, for example, F1 or F2, and just produces for you some evaluation of that. And let me just write F1 of X for shorthand for the evaluation of F1 of X. All right, so sort of informally, privacy, right? It's that F1 and F2 individually reveal nothing about F, and there's a linear reconstruction property that the sum of the individual evals is equal to the original sort of evaluation of the function. And so, like I said in the previous slide, right, FSS can be realized for simple classes of functions, under the existence of any sort of one-way function, any sort of symmetric key crypto. So for example, point functions was shown in the original paper by Neve and Yuval, and then interval and decision trees, later on in the extension by Elet, Neve, and Yuval. And there's sort of many interesting applications in the two-server model using this kind of linear reconstruction property that function secret sharing has. And these were pointed out in this sort of these lines of works. So in particular, for example, private read write, right? So it provides an analog of the classic information theoretic two-peer reading or writing into a computational version of it, or even like an oblivious RAM kind of thing for it, right? So this was explored. This was sort of introduced in the original sort of Gilboa ASI paper, and then more recently optimized in papers such as the Riposte paper, Splinter, and then this Dorner-Charlotte on distributed oblivious RAM, and then a recent follow-up work by Bunn, Katz, Kushilevitz, and Ostrovsky on sort of how to further optimize that. So there's interesting applications there. Many other applications such as keyword search, distributed histograms, and then relevant for us, right? Private set intersection and private membership, private set membership. So this is the approach that we'll be taking, sort of following that line of work. All right, so now let's go in and look at a warm-up example, right? We have the pieces that we need. Let's see how a simple example of how we can put them together. All right, so just as a sort of comparison, because the EPI1 solution also kind of used function secret sharing, we wanted to sort of contrast a little bit. And so one instantiation in that paper, they have the client, they have this sort of servers 1 and 2, and their solution, first they perform this kind of Diffie-Hellman-like shuffle, and then they run two-peer using function secret sharing. So in our solution, what we do is we actually, we also take this sort of two-server approach, but it's observed that function secret sharing can be directly applied to sort of build private set intersection, right? So on the left, I should have mentioned that this was to sort of build like a private set intersection protocol. We can sort of do that directly using function secret sharing, right? There is just this sort of direct transformation. There is a slight sort of subtle difference if you want to be fair on the comparison, which is the actual way that you use function secret sharing, right? The key size is proportional to input length. And so if you're just trying to retrieve a record, let's say from a database of size n, those keys are proportional to the length of the input, which is just an index into n. So that's like log n. Whereas if you're doing this sort of directly on the tokens themselves, the key lengths are proportional to token size, right? So there is a discrepancy that I'm kind of sweeping under the rug here, but in sort of full fairness, right? There is not all FSS keys are of the same length. So what does our warm-up solution sort of look like, right? I think, like I said, right, what the phone does is it creates these point functions where the secret point is the token, and the secret value at that point is the weight, right? So given one of these tokens and one of these weights, we just sort of view it as a we just sort of view it as a function, right? It's a function that takes on the value 5 if x is that token and 0 otherwise. Obviously, the succinct representation of that function is just token comma 5, and this sort of gets fed into FSS gen, right? And what this produces is these two functions f1 and f2, or these two keys f1 and f2. That is a secret share representation of f. Okay, so that's sort of the first step, and the client does this for sort of every single token, and then the second step is when we actually want to do the tracing, right? So and again, sort of just in comparison to like the Google Apple solution, right? The infected upload kind of follows a traditional approach, right? Someone goes to their healthcare provider, they determine they're infected, and the tokens that they have generated gets uploaded into this database, right? So there, the uploading, sort of the infected token contribution part, that sort of still follows a traditional approach. Here we're talking primarily about the tracing, right? So for tracing, the client performs this FSS key gen on all of their tokens, and so this is one of them on this token, one of them on this token, and they basically get just a bunch of sort of private queries. And there's the F1s on top, and then the F2s on bottom. These come together to form an aggregate query. It's not anything special. It's just the list of all the private, of all the F1s. And then for the F2s, these all sort of go to server 2. And for the ones that go to server 1, what does server 1 do? Right? The server has a bunch of tokens. And what they do is just eval and sum over all queries and all tokens, right? So for every single one of these queries here, and for every single one of these tokens here, you're going to do an eval, and then you're going to sum up all the results. And so the response is actually a short response, right? It's just a single secret shared sum, where the secret sharing is actually between the server 1 and server 2 that does the same thing on the on the sort of the other side of the page, and they both give back a single short response to the client. Okay, so let's take a look at what this looks like sort of algebraically, right? Recall this sort of functionality that we're trying to achieve here. The protocol to actually sort of we just sort of put down in pictures, for each token that the client Alice has, define the point function PI, which is just PI is equal to PI of xi is equal to the weight at xi and 0 otherwise, and to run gen for each of these point functions, right? And then you get these two keys out, and then you send the set of keys, the first keys to the server 1, and then the set of second keys to server 2. And then the servers compute the sum over all infected tokens over all of the different sort of phone queries, right? So there are n of these keys, and there are little n of these keys. There are capital N of these y values. And here I'm just kind of graying out the weights on the server side. We're just assuming that there's no weights on that side. We sum them all up, and then we send back this single response to Alice. And then after that, Alice just reconstructs the answer, which is just response 1 plus response 2. All right, so actually, this is a fine print here, right? The these these evaluated sums might actually reveal something. So the two servers should have like a correlated nonce that they blind it with before they send it back to Alice. Fine print. So just a quick analysis of this solution, right? The correctness can sort of be observed by linearity, right? So you have one server summing up all of these on the left side. You have another server summing all of these on the right side in red. And when you sum them together, you just move all of the all of the point evaluations into the sum, and then they recombine to the right thing. In terms of security, we look at security in the standalone semi-honest two-server non-colluding model. And there again, informally, right, you can simulate the view of the servers because all they get are these FSS keys. And then the view of Alice, right? Alice only gets back a single number from each server, and if it's actually genuinely being blinded by a fresh random value, then she basically just gets two random numbers, and the only relation is that their sum is the answer. So that's also sort of very easy to simulate. And then let's sort of look at the cost, right? The communication, Alice sends n of these keys to each server, and the server sends back one group element. So far so good. But what about computation, right? Alice performs n of these gens, but then the server work, right, has to perform something like n times n, work evals, and then the sum of cost, the sum of the cost of summing them all up, right? And this is what we're hoping to reduce, and what I'll show, sort of how to reduce for the rest of this talk. And the approach follows a similar approach to sort of these hash-based PSI solutions, where you're able to not have to do all this sort of quadratic mixing and matching, right, or all possible combinations. So that's what I'll sort of go into next. All right, so this is the situation at hand, right? From just a high-level perspective, right? You have these keys that are generated by the client. You have these tokens that are sitting on the server side, and you want to, you have to evaluate every single token on every single key, right? But you don't need to, do all possible combinations. You can sort of do some work ahead of time to avoid this, right? Which is to say, I mean, the sort of obvious approach here, right, is to do sort of bucketing by hashing, right? So the client places the keys into buckets where you hash not the keys, but the tokens used to generate the keys, right? And then on the server side, right, the servers then hash their tokens into the buckets. And you know that if two things didn't land in the same bucket, you don't need to waste time doing this comparison, right? So if you just sort of do this bucketing approach, for buckets of size b, now this drops down to sort of b times n server work, b times capital N server work, and then you'll need to send sort of b times little n communication. All right, so how do we sort of exploit these sort of unevenly balanced buckets, and how do we actually make sure that things don't overflow, right? Because that's sort of a problem here, right? So if you just use ordinary bucketed hashing, if you just choose your bucket size, large enough, that should ensure no overflow, right? So that immediately gives you a solution which drops from little n times big N to sort of log little n times big N. And with a cuckoo style hash, we can further improve this. So rather than so there are many great techniques in the sort of literature of hash-based PSI. Rather than sort of taking those techniques and applying them, we actually considered a streaming solution, right? Because if you can query multiple times per day, you just want to know sort of eventually what when you're getting, not necessarily immediately. So to get constant size buckets, the client can just you can just clamp the bucket size down to something very small, and anything that overflows, you just sort of cache, right? You say, okay, I'll send the next day or the next sort of intersection period. And this is kind of in contrast to cuckoo hashing with stashes. In those approaches, you actually keep the stash and use that as part of your PSI. We're saying anything that overflows, let's just take it out of the PSI, right? So we're sort of giving up immediate correctness for eventual correctness. And there's sort of two ways you can do this. You can choose you reuse the same hash function. You can use different hash functions, and we can sort of analyze what's the average and worst case wait time for something to actually get taken into this into account for this PSI. And as sort of a side note, right? We want to ensure a couple of things, right? One is that the client cache doesn't grow indefinitely, right? If more and more things overflow, you have to put the things that overflowed into the next day. So how do you know that doesn't just sort of explode off? And secondly, we want to make sure that the tokens get sort of a good cycling period, right? So we want to make sure that this is things don't wait too long for it to get processed. So this can actually be viewed as a sort of like a queuing queuing problem. So just I can quickly sort of summarize the results, but for the details you have to sort of look in the paper. If you have these sort of parameters, number of new client tokens per day, bucket size, number of hash functions that we want to use, and whether or not we we choose a different hash function every day. We actually tried this out experimentally, right? Where for one hash function, for two hash functions, and then for sort of different different parameters. For example, using bucket size of 2, 25,000, sort of the token rate, and also sort of the fill rate. You see that the actual wait time is reasonably small with 1, and then with 2 we can really drive that down. And this is both in the case of a concrete number, but also as we did experiments with larger and larger n, it kind of steadied out to roughly the same sort of wait time. Okay, and then we sort of also performed an asymptotic analysis on this wait time, where for one or for more than one hash function, you have you have an average case and you have worst case that grows reasonably nicely in the number of tokens, right? So for the sizes of tokens that that they were sort of that they were sort of playing around with here, right? The experimental results, I think, say that it's good. It's sort of good enough for many applications, and then asymptotically, we also have sort of analyses that show that they sort of behave well. All right, but the details of this you can look sort of look for more in the paper, and so with this streaming, right, what do we get, right? So we have now this sort of PSI weighted cardinality in the streaming model, where the performance, right, the client sort of performs C times n hashes of tokens, and generates, right, you potentially hash each token C times, right, and you figure out which bucket they should go into. They then generate, for each bucket, and there's n buckets. For each bucket, you generate B FSS keys corresponding to the things that landed in that bucket, and also dummy keys for the case where there's some empty slots in the buckets. And then you send those that many keys to each server. And then on the server side of things, right, because it doesn't know which bucket or which hash a particular token went into, it tries all hashes, right? And this again is reminiscent of the idea of from hash-based PSI, like for example the phasing paper, where on the server side of things, because it doesn't sort of know where it potentially landed up in, it has to sort of try all the different hashes, and then it does the evals on all of these, right? So in the end, right, B times C again, like on the previous slide, they can be really, really small, like 2 each, right? So this is like 4 capital N evals, and again sums them all up and sends back one group element to the client. Okay, so that pretty much covers our sort of PSI weighted cardinality result. And now let me talk a little bit about architecturing that sort of crypto tool into sort of a larger solution. Right. So first, let me talk about the FSS implementation itself. So this is an implementation of BGI 16. This is the CCS paper, and we wrote this in C++ with several optimizations. In terms of the PRG, we actually so we actually allow for sort of compile time or runtime selection of interface sizes, right? So if you wanted to do, like, if you know ahead of time your tokens are 128 bits or 80 bits, if you just specify that at compile time, you can sort of further optimize some of the some of the code. For the PRG, we actually use like a fixed key AES. This is like the correlation robustness approach that's taken in work such as the Splinter work, and also a recent work of showing how to use fixed key block ciphers for crypto, and there you get sort of an additional savings where you don't have to rekey the AES again and again. Although I think in some recent works it's shown that if you carefully pipeline your keys, it's even the regular building PRG from non-fixed key AES has really good performance. So, but at the time we're sort of implementing this, this seemed to be the sort of the fastest approach, and it was also sort of taken in a couple of previous papers. We had an API for sort of batch generation and eval, and had a couple of language streams. If you didn't want to use C++, you want to use something else. And the whole reason for batching here, this isn't what this is for sort of batching across multiple clients. This is really just for batching for even just a single client, right? Because there are still a lot of things that you want to sort of gen or eval on, and this batching really is just to reduce repeated calls to the library, right? You just want to make one call and it'll just generate a whole bunch of stuff for you. This was cross-compiled and benchmarked on iOS, Android, Linux, and we also plan to sort of have this open source. So this is this will show up there soon. All right, so that's sort of the FSS implementation, and then what about sort of putting it all together, right? An integrated solution that takes this FSS, puts it into a PSI sort of weighted cardinality, and then also sort of ensures that this whole thing works on a phone, right? So I can talk a little bit about this, but really this was some great collaboration with CryptoWire, where we actually had like an integrated steel thread test. And there's lots of engineering that sort of had to be done, both on the phone side of things and on the server side of things. And I'll give you a little flavor of that in over the next couple of minutes I have. So, in terms of the upload side of things, right? The infected user side of things, right? This approach looks similar to the Google Apple the GAIN architecture, except we have these two servers, right? So, but we don't actually want the client to actually talk to both. The client will just send to one server, and that server just gets replicated. And then for the tracing side of things, right? Again, this follows very similar to the trace of FSS, but again, making sure that all of these things are properly coordinated, and that you sort of get back the results corresponding to that client's queries. Again, careful sort of engineering had to be done there as well, right? But this overall flow is indeed very sort of reminiscent of the flow sort of prescribed in the PSI-CA solution. All right, so and then finally we sort of leverage a trusted execution environment, right? So there, instead of protecting against a malicious client using additional sort of crypto primitives, like for example, forcing them to do zero knowledge proof, we protect a lot of that just by leveraging, okay, well, assuming you have some sort of TE on your phone, there you can sort of ensure good behavior by just making sure that the appropriate things are done within that environment, rather than using sort of other crypto to sort of harden against malicious adversaries. And in terms of situational accuracy, right? There are sort of improved sensors and sort of different modes to ensure that when you actually receive a token, you're able to, based on a variety of factors, including things like location, things like signal strength, et cetera, be able to sort of assign a context-aware risk score. And this is not necessarily just from one sensor. This is potentially from multiple sensors. And there's a lot of sort of experimental work that was sort of done here to sort of appropriately tune these risk factors. And overall, right, having sort of chipset level access to these sensing environments and with this sort of raw sensor data actually allows for quite accurate sort of decision making for what whether or not you actually think that this encounter contributed sort of more or less risk. Again, the details of this are in the paper, but this is just sort of a high level summary of what what the engineering sort of efforts were in terms of actually getting the weights associated to each of the tokens. And then in terms of addressing these confidentiality and integrity concerns, right? We want to make sure that we protect against data pollution, replay attacks, relay attacks, devices performing arbitrary query lookups, arbitrary lookups, right, where they just sort of ask for whatever, and also sort of various sort of man-in-the-middle attacks. And by and large, these are addressed by having this TEE. So there we were able to sort of save on having to use sort of more heavier weight crypto, just from this just by leveraging this sort of trusted hardware. And sort of finally, right, just to sort of draw out the trace, and again, more details of this are in the paper. There's we have this trace diagram for sort of reporting an infection, and then in the interest of time, I'll just sort of skip past this, and also the sort of the querying trace. All right, so just as a one slide summary at the very end, right? Comparing this to sort of other contact tracing solutions, right? There are solutions where you might want to just reveal all infected tokens. There are solutions that only reveal counts. There is kind of the ideal solution that reveals just a trusted yes or no. But we're looking for something that's that provides a richer sort of result in terms of weights, and also have the privacy where you don't, where the clients do not learn the infected tokens, they only sort of learn the result of the weighted size of the intersection. All right, so with that, I will conclude. Thank you.